My name is Wojciech Macek. I work in semi-house. I'm also a FreeBSD committer, and today I'm going to talk a little about the latest project we did, the port of FreeBSD to the IBM POWER8 architecture. For all of you who are not familiar with what the semi-house is, so the semi-house, the company I'm working in, is a typical consulting company. So some time ago, a client came to us and he said, well, there is ongoing project in FreeBSD. There is some proof of concept work done for providing support for PowerNV. Basically, it's working, but we require support for PCIe and some improvements in stability stuff. 95% of work is ready, they said. You only need to do 5% of the missing part. We said, why not? It's a quite nice project. But when you have a client and anyone tells you that something is 95% ready, don't believe. This presentation, the whole presentation will be about this mythical 5% you are working on. I have divided this presentation into two parts. First, I would like to describe what is the PowerPC, what is POWER8, what is PowerNV. And then if we define some words, some sentences, we can go further and I will describe actual work which we did. I call this part bugs, but it's not some kind of bugs the developers are seeing every day, some boring ones. I've prepared a list of 4 very quite challenging, quite interesting things, which I think every one of us developers find useful in their work. And also I have some performance benchmarks which all of you who are interested in PowerPC, PowerPC 8 might find useful. So let's start. On the courtesy of IBM, I have their slide from the marketing presentation. This is the POWER8 CPU. This is the chip we were working on. I don't want to go into details because this chip is pretty similar to whatever chip we can find in the market nowadays. It has 12 cores. What's interesting, each core is able to process up to 8 SMT threads. So 12 cores give us almost 100 virtual cores in the system. It has also L2, L3 cache, PCIe, integrated PCIe controller, DDR controller with up to 230 gigabytes per second of total throughput. So this chip is quite powerful. Its main purpose is to be used in the data centers, and the goal of the IBM is to compete with POWER8 architectures with Intel Xeon. So, not going into details, I found this thing differs the POWER8 from the Intel chips. So the IBM decided to provide level 4 cache between DDR and the CPU itself. By between, I mean literally between. The L4 chip is a physical chip located on the PCB and is located between DDR and CPU interface. So for all of you familiar with Intel 386 or some other ancient times, there's a similar approach which IBM implemented in the POWER8. If you're asking me what is the impact of the performance, well, I don't know. I was very interested in checking how the L4 off-chip L4 cache behaves, but unfortunately on POWER8 it is impossible to disable this thing. So I couldn't run any comparison tests to see how does affect the latencies, the cache hit ratio, or whatever. The only materials I can rely on, they're official materials from IBM, which they say it works pretty well. So if you have any questions, just ask IBM. I said a few terms before POWER8, PowerNV. So on this picture, I presented the complete software stack which is used in the generic POWER8 or PowerNV or PVM system. So when you buy the POWER8 chip, it usually comes into a rack-mounted server form factor, it can work in two modes of operation. On the right, I start from right. On the right, we have typical use case which is implemented in data centers. The power server is a host for the virtual machines. In this scenario, we are running KVM or any other hypervisor on the POWER8. And the guest applications are virtual machines, and this is something the user operates on. This mode is called Power KVM, and the FreeBSD was already able to be run as a guest in Power KVM infrastructure. On the left side, there is a PowerNV. PowerNV, it stands for Power Non-Virtualized, which means that the operating system is working on the bare metal directly on the hardware. For example, on my laptop, I have Ubuntu NV, and because it works directly on the CPU. So the same idea is used by IBM to differentiate between virtualized and non-virtualized type of operation. Also, you can find the complete software stack which IBM offers. At the very bottom, we have the POWER8 hardware accompanied with something called FSP. FSP is a small coprocessor which is used for health management, for power management, for providing the console over the network. What's very interesting is the middle layer between Linux and the hardware. It's called OPAL. OPAL stands for Open Power Abstraction Layer. This is a kind of a hypervisor which works in a hypervisor mode. It has well-defined API. It is used to separate the Linux from the hardware it operates on. So having the standardized API of OPAL, Linux should not be aware of the hardware which is lying underneath. For example, we can replace POWER8 with POWER7 or POWER9, and we still more or less are supposed to run the same Linux distribution without any issues, because OPAL is an abstraction layer and provides all the interface with the operating system. This is what I already said. The FSP, it's not very interesting, but the OPAL lib library, the hypervisor which is working on the PowerPC POWER8, is required for managing almost everything. If we want to configure the interrupt, configure PCIe, have a system console, for example, we need to perform a hypervisor call up to the OPAL to ask him to do something for us. So this is some architecture which IBM relies on, and we can't avoid using OPAL at all. Yeah. And that's the baby we are working on. This is a S821C system. It's one new rack-mounted server board dedicated for CPU-intensive operation. It's equipped with 2 CPU nodes. It has 128 logical cores, and 8 CPUs per 8 SMT threads per each core, and 2 sockets giving 128. It has a bunch of RAM and Intel SSD, along with the Chelsea 45 gig network interface. And the goal of the project was to provide support for all things which are visible on this slide. Yeah, before I move forward, I would like to tell a little about PowerPC or Power64 architecture in general. I don't want this part to be a comprehensive tutorial. I'll concentrate only about pointing differences between PowerPC 64 and any other architectures which are broadly used, like ARM, like Intel. So the first thing which I would like to show is to prove that the PowerPC 64 is a typical RISC CPU. If you take a look on the registers it offers, it's very similar to what we find nowadays in, for example, ARMv8. It has some registers dedicated for function parameters. Some of them are used for storing variables, being non-volatile registers, and some of them, by convention, are used for special purpose. And the first one is the R1, which on PowerPC 64 is a stack pointer. The second one, which is very different from other architectures is R2. R2 is something called TLC pointer. TLC is something that is specific for PowerPC 64. It's called a table of contents. It's a type of a dictionary very similar to the virtual function tables found in C++, which is responsible for the dynamical relocation of the function and for performing function calls for position-independent code. I will describe it a little later because this thing is quite complex and I think it's worth being noticed and worth being remembered while writing software on PowerPC 64. The one register which is missing here, which is also worth being noticed, is the program counter. On PowerPC 64 we have no direct access to PC, so for those of you who are familiar with, for example, ARM architecture, this is something which really is a pain in the butt when writing a code in assembly. But on PowerPC we have to live without it. I said TLC. So the TLC is a dictionary which provides mapping between function name, the symbol defined by the linker, and the place where the function actually is located in the memory. On the typical architecture, when the developer creates, for example, a function print, the compiler and the linker create a symbol print and put it somewhere in the memory. Under this memory location, we have a print code. This is not the case on PowerPC 64. On PowerPC, the print symbol is just an entry in the TLC dictionary. And the place where the print function is located, actually, where the code resides, is a place in the memory called .print. This is because when we have a table of contents, we can easily relocate the whole binary. We can, while doing dynamic loading of the ELF, we are looking for the TLC base and we are recalculating the addresses visible there to match the place where the binary is actually located. This to provide the position independency of the mode of operation of the code. The problem is that the TLC table has a lot of limitation. For example, it cannot exceed 64 kilobytes. It must be within 64 kilobytes in the same segment of the memory where the actual function is. So when we build the FreeBSD kernel, which on PowerPC, on PowerNV is about 20 to 30 megabytes, we end up having thousands, like 10,000 TLC tables. So each function which we have in the system has its own TLC table which it used. So while if we are doing a function call, we also need to replace the TLC table and replace the R2 contents with the new TLC table required by the function we are calling. This is shown with more details on this slide. While, for an example, I've chose well-known print function. In normal architecture, I'm not saying that the PowerPC is not normal, but in the other architectures, the call for print, it would be just one opcode in the assembly. On PowerPC, there is 6 of them. First of all, we want to call the print, take a look on the right side, we need to store the current R2 pointer somewhere on the stack, because it might get corrupted, so we need to remember its value. Then we need to load R2, we need to load the virtual address of the .print function we are going to jump to. Also, we need to modify R2 with the new TLC table pointer valid for the new print function, and then we can perform actual jump. I mean, we use the CTR register to store the 64-bit address and run BLCTR. It means branch linked to CTR register, which jumps execution to the print table, the print function. Once we go back, we need to restore the TLC from the stack just to provide the same environment for any other operations we could call further. The other thing which is strange on PowerNV and PowerPC in general is the IOMMU requirement. The IOMMU is a special subsystem, usually, as far as I know, only used for virtual machines. For example, if one has a virtual machine and want to pass the network cards directly to this machine using something called like PCI pass-through, he or she needs to use the IOMMU. And that's the only case where the IOMMU is necessary. That was what I'm thinking since the work for POWER8. Apparently on POWER8, it's required to be enabled by default because without IOMMU, the PCIe doesn't work at all. This is the example of the POWER8 internally, how it works internally. We have DDR, which is a system memory, accessible by a system bus. We have a CPU and we have NMU. With term NMU, I think all of you are familiar. It's used for address translation between the virtual addresses which CPU operates on and the physical addresses required by the system bus and DDR. So the IOMMU is a very similar piece of gear, but it's used only by PCIe devices. So if PCIe device wants to access the DDR during DMA transaction, this request can be translated and routed to maybe some other part of memory or blocked if the transaction is not supported, or you can do with anything. On POWER8 and all further powers like POWER9 and everything above, the PCIe devices can be assigned to one of many, 256 partition elements. The partition elements, each partition element contains one IOMMU. So we have up to 256 groups, partitions, which we could divide our PCIe devices into. This is very useful when we have virtual machines and we want to provide decent isolation between them. We can just, instead of using one IOMMU table, we can use several of them, each for one virtual machine which is running on the system, which is quite good. On FreeBSD, on PowerNV, we are not using VMs at all. So in current implementation, every PCIe device is mapped to IOMMU partition 0. And IOMMU is enabled, but it's providing one-to-one mapping to the addresses of the system bus. So from the developer perspective, it's non-existent, but it's enabled. Yes, and that is the point where we started our project. The initial investigation showed us that more or less the PowerPC 64 and PowerNV port is pretty much working in QEMU. Thanks to the Nathan Whitehorn, who was responsible for creating the PowerNV project branch, most of the most difficult things was already done. I mean, the MMU was working, the system was booting, even sometimes was booting to SMP in multi-user. So the status was pretty impressive. So this is what the client also saw, and this is why he thinks 95% was ready. The only missing features we identified at the very beginning was the missing PCIe driver, which makes the PCIe bus unoperational, and also identified some things which had to be changed in the FreeBSD loader to support mixed NDNS configuration. In PowerNV, the loader is being run as little endian, but the kernel, FreeBSD kernel, is being run as big endian. So we have NDNS switch during the loading, so that's why some work had to be done to the loader itself. Of course, there is a lot more that meets the eye. We found that there's a lot of places in the FreeBSD which had to be modified, had to be fixed. Some of them were PowerNV specific, but a lot of things we found there were in FreeBSD for ages. But somehow they became visible once we added POWER8 support. So this presentation is also a guideline for all of you how much work the developer can expect for providing a decent and stable support, even for a piece of existing code. The proof of concept is just the halfway to the success. Yes, and going to the most important section, it's bugs. I've prepared 4 of them. Of course, we were dealing with a lot more, but I tried to choose the one which are quite easy to be explained, and the one which you as a developers quite useful in your future work. Maybe if you try to avoid them, the FreeBSD we are developing will be constantly getting better. Yes, this is the first one we were fighting with. It took about 3 or 4 weeks, this one. We had a very nice observation that in scheduler switch routine, the kernel sometimes was panicking at the cursor. The MPass routine, which checks if the log pointer is valid. So just after the CPU, just after the thread was activated on the CPU, the first thing the scheduler does is it does some sanity checks. So the first sanity check failed. What was very interesting that the reproduction rate was either 100% or 0%, depending on the build we did. For example, adding comments to the code made the issue disappear. And that was the first time I ever saw such a situation. Adding comments. Who would think so? This time I spoiled it a little because you can see a header TOC change in context switch, so this is actually explanation of what was going on. But it was, I assure you, it was really hard to find what is the root cause of the issue. So I prepared a stripped down version of the sketch switch routine. We can see that after the CPU switch is being done, we are starting with a new active thread. We are loading some CPU ID, some thread pointer, TDQ, and doing this famous MPass. So we spent a lot of time debugging C code, and we found that there is nothing wrong with either the scheduler or with the scheduler switch or with any other routine which is in the system. So if you do not know what to do, look into assembly. If it didn't help, at least look professional. So this is what we did. And we find that there was an issue with the TDQ itself. It looked like a TDQ pointer was pointing to a different part of memory. As you can see from the define, TDQ CPU is a global table. And as a global table, PowerPC 64, it is accessible by a TOC dictionary translation. So if we have a TOC which is messed up, for example, if it's R2, a TOC table is used, is set as not for the function which we are expecting to be, we just could access some random part of memory. This time we were very lucky because we detected this with cassette. But if the cassette was not available here, we will probably end up with random memory corruption, which would be impossible to find. This is what was going on. Before CPU switch, we were R2 and TOC set up for required by the CPU switch routine. And then we were calling the CPU switch, which is a very ugly function. It does everything what the function should not do with stack frames, with registers, but it's required because the CPU switch, its intention is to switch the context. So it's expected that this function heavily operates on stack and on system registers. So this function was not restoring stack frame correctly. And just when the CPU switch returned, the scheduler switch, the parent function, hit the R2 register set up to point to a TOC table, not for the scheduler switch, but for the CPU switch, which is something different. And this is why it didn't work. We tried to, the code tried to access TDQ using the wrong value of R2 TOC, and got some random piece of memory which didn't contain the valid TD log, and this hazard failed. So the question is why it worked for years. It worked for years because the PowerPC 64 linker is quite intelligent, and it tries to optimize the number of various TLC tables in the system. So for all these years before, the bug was present, but was not visible because scheduler switch and CPU switch were using the same, exactly the same TLC table for operational. So once we added the PowerNV support and binary become larger, these two functions were too far away, and the linker had to use two TLC tables. So this is why we saw the issue during the content switch. Also, why the adding comments made any significant difference. I don't know. I only can suspect that it's because of we're running parallel builds. And if we are doing parallel builds, something was building faster than something else, and this intelligent linker didn't exactly know which TLC table should be split and which TLC table should be stayed in one piece. So this is why it's something that did compile successfully and worked, and sometimes it didn't. Yeah, the next bug is a reprimand for all developers, including myself. As I said, the PowerPC 64 is a big endian system. So once we get to the point where the PCIe was up and running, we're trying to attach any drivers which were on the system. Unfortunately, there was only one driver which worked. It was XHCI USB interface. All other drivers which we are trying, they were either failing during attach or didn't work at all, or some drivers even panicked the system. So there is a huge lag in the development of FreeBSD drivers. We are not, as developers, we are not thinking about some other exotic architecture which our code could be run on. For example, the best example I found is the NVMe driver, which was written beautifully, really. All registers were abstracted using bit fields. The code was clean, visible, readable, and it looked just great. But there is a problem with bit fields. They are not portable. When we switched endianness to being big endian, everything was messed up, and the NVMe didn't work. Actually, we also studied the C specification, and from what we found, the little endian version worked only by accident. Generally speaking, please keep in mind, bit fields does not guarantee anything. So if you have a chance to use them in your drivers, please think twice. Maybe there are a better way to do the same. So fixing the NVMe required us to go back to the generic stuff and the typical approach to access registers. I mean, using masks, using offsets, logical shifting, and NDNS conversion. Of course, the code now looks a lot worse than the code using bit fields, and it's not something very proud of, but actually it works. So the NVMe, this change of bit fields requires, this number here is wrong. The newest patch after the review has about 3,000 or 4,000 lines of code which had to be changed in NVMe to be big endian compatible. There were also some good examples of drivers like CXGBA, which was from the very beginning was prepared to be run on big endian. However, it was not tested in this environment, and it has some few needs which we identified, but generally speaking, it was like 2 or 3 lines of code which had to be changed to make it operational. Yeah, the third one, edge-triggered interrupts. If you have a system, if you ever encounter a system with edge-triggered interrupts, I'm 100% sure that sooner or later you will fall into troubles. This is the very advanced test scenario we are running. It's the Aper3 over CXGB interface. After a few minutes, the traffic stopped. The reproduction rate was 100%. I mean, every few minutes, maybe a few hours, depends on the test, but eventually the NIC became unresponsive. We're suspecting a network stack issue. We're also cooperating with Navdeep Prahar, the maintainer of the CXGB driver. But eventually we found that the interrupt delivery was messed up. At some points, the interrupt stopped arriving. So we dig into the interrupt routines. And we draw a case how it should look like. And this is how it actually works in the Sunday scenario. So let's go from the beginning. Let's assume we have a device which wants to send an MSIX interrupt back to the host. So the first thing it does, it sends a special PCI packet which asserts the MSIX pending bit on the PCIe host controller. Then the host PCIe host controller put itself in a state called MSI in service. It's mostly because we don't want to have the MSIX storm and we need to stop the arriving of next MSIX for a while. So this is why the state is necessary. And then it asserts the CPU IRQ line, which allows the CPU to execute the handler. In this case, we run the handler, mask the IRQ line, because by FreeBSD specification we need to have IRQ line masked while we're executing ithread. And after the masking line, the CPU reset handler clears the MSI in service bit in the PCIe host controller, just to allow further MSIX to arrive to the system. Next, the ithread is being executed, and after everything is completed, the IRQ line is being unmasked to allow next interrupt to be handled. This looks quite good. However, it has a race condition inside. There is a problem with between leave MSI in service block and unmask IRQ line block. The execute ithread might take a while because ithreads can sleep, they can be some CPU intensive. So the time when we spend in the execute ithread is quite significant. It's showed up that if the new interrupt arrives just in the time when we are executing ithread, I mean between the leaving MSI in service and a masking interrupt, we will end up in the locked state. It is because the PCIe bus controller tries to send the IRQ, try to assert the IRQ line as soon as the MSIX arrives. However, at this point, we have IRQ line masked. So this is why we are losing the interrupt. If the interrupt was level sensitive, this situation wouldn't happen, because when we unmask the line, we could see that the interrupt is active, and we just could jump back to the CPU handler and serve the interrupt once again. But while having them edge triggered, the assertion of the IRQ line happens only once. It's a single shot. So if we missed this particular point, we lost this interrupt forever. So this was quite easy. For us, it took only 2 or 3 weeks to find. The fix was also very easy. We had to unconditionally leave MSI in service mode after the unmasking IRQ line. Generally speaking, it doesn't do anything if MSIX didn't arrive in that period, but if it did, it made the controller leaving MSI in service mode. And when the controller leaves this mode, he sees, oh, I have pending bit set, no one serves this interrupt. So the controller sends the edge triggered interrupt once again, and then the CPU is able to handle it because the IRQ line is unmasked. So with this fix, we were able to run very long stability tests, like 2 or 3 weeks without a single crash. To answer your question why it was difficult to find, this situation happened only once per 1 or 2 millions MSIX which were sent from a network card. So it sometimes took a few minutes, sometimes took a few hours to reproduce the case. Yeah, and the last one is the newest one. We have pushed the fix 2 weeks ago. And the test case was pretty similar. We had an hyper-3 running over a loopback interface. And so we compared the Linux with FreeBSD. On Linux, we got 70 gigabits per second, while the FreeBSD were not able to exceed 600 megabits. Yeah, what a piece of junk, right? We're trying to investigate it. Maybe it was the network style which is poor, or maybe some, I don't know, context switches are taking too much time. We have run D-trace on this, but nothing was suspicious until we get back to the very beginning and we implement a very, very simple test. We created a loop. We created a loop in the assembly which was literally doing nothing, but we're measuring how much time does it take to execute 4 billions of iteration. And it showed up, and there is a difference. We were comparing Linux with FreeBSD, and it seemed that on FreeBSD, after we enabled the SMP, we have some troubles with the speed of instruction execution. So we were very excited because it's a kind of bug which every kernel developer thinks it's like, whoa, I need to fix it. But none of our approach succeeded. We were looking in page mappings, looking into some caches are enabled, but everything was just fine. So we were resigned, almost. But some time ago in the swimming pool, I just thought, 5.5 seconds, 45 seconds, why is it 8 times bigger? I got back to the work the next day, and I ran another various benchmarks, and every single time I did some benchmarking, I found that the FreeBSD is 8 times slower than FreeBSD. FreeBSD is 8 times slower than Linux. And that was really interesting because 8, it's not a 3.567 or something, it's just 8, it's almost equal 8. I know that it's the power 8, and maybe it's 8 times slower, but that's not a good explanation. So going through the documentation, and voila, we have 8 SMT threads per each CPU core. So maybe this is the case. And that was a perfect shot. On FreeBSD, when we are starting the SMP, the first thread which is activated on the CPU is an idle thread. So its purpose is to be a placeholder if the CPU has nothing else more important to do. It is executing idle thread. On the PowerNV, we need to tell the SMT scheduler within the same SMT group that this core is idling. According to documentation, we need to send a special instruction to the SMT scheduler. It's a kind of NOP operation. It's CPU spin rate, which is supposed to do yield. The yield means that this particular SMT thread releases all the resources it's been using and gives the CPU power to some other SMT threads within the same group. We were pushing some back and forth emails with IBM and found, after a few weeks, well, not really, a few days, we found the answer, oh, we forgot to implement this. So the CPU idle thread was interpreted by this SMT scheduler as a very, very important task. And the SMT scheduler was dividing the resources it has equally. This is why we had 8 times slower performance compared to Linux. Unfortunately, there is a second shame on you, IBM. We tried to use a similar approach as we did on RV8. I mean, in a CPU idle routine, we wanted to put the CPU to the sleep mode just to be sure that it doesn't execute anything. And the PowerPC, PowerNV, PowerPC8 supports this, of course, but in a very, very awkward way. On the left side, I've included the instruction WFI. It's an acronym for wait for interrupt. It's the instruction from RV8. It's very simple to use, it's very convenient. It just stops the execution and removes the power from the CPU and waits until the interrupt arrives. When the interrupt arrives, it just continues execution from exactly from the same place. So it's very useful, and I don't know why IBM decided not to implement this instruction this way, but they didn't. In fact, we had to implement a new reset routine for the CPU because when the PowerPC8 CPU wakes up from the sleep, it goes exactly through the same path as it does during boot up. So the reset routine needs to be aware that sometimes the CPU might just be started, but sometimes it might be just woken up. So lack of this small assembly opcode required us to write like 1,000 or 1,500 lines of code just to work around this issue. But it helped. The performance went back to normal, and we, with this fix, we were not to see any differences between Linux and FreeBSD. Yes, the current work. All work that we have done is already merged to the head. So for all of you who would like to test the PowerNV for yourself, you can just grab the head from SDN, build the system, and it should just work fine. Here are the things which are supported and are tested. We have the full system support, CPU, integration with OPAL and the console interrupts. We also support some of PCI devices. Of course, not all, but we can guarantee that XHCI, NVMe, and Chelsea CXGB NIC are operational. Also, some power management is working fine, so it's quite a decent state for the platform, I think. There is also things which doesn't work. First of all, there are a whole bunch of various drivers which will not either attach, or maybe sometimes they don't work because of differences in NDMS. One of the drivers which doesn't work is HCI, which we couldn't make operational on PowerPC8, and also the whole bunch of Intel NICs because they are using eFlip. eFlip is not big NDM safe, so they don't work. Also, we have some plans for fixing dtrace because right now it crashes or it doesn't show meaningful data. This work is scheduled, of course, and it will probably be finished maybe in a few months, I think. Also, the big point is to optimize the libc to utilize SIMD instruction. Right now, the big side effect of using OutGCC 4.2 is that we have no support for decent PowerPC8 CPU. I mean, the compiler is able to generate the generic PowerPC 64 code, but the code is not optimal for this CPU. So we can see some performance degradation due to this one. Also, we have a Power9 project in the roadmap, which covers several interesting aspects, like providing FreeBSD support for little endian. So that will eliminate the need for replacing drivers and provide the compatibility with other architectures, which all of them are little endian. And also, there is a plan for replacing the MMU tables to use radix page tables similar found in Linux. Because Power9 is the first CPU which actually supports hardware radix page tables, so they are support hardware, so we can use them efficiently in FreeBSD. I also have some, we have some time, so I also have some data to present about the performance we got. So I've prepared 2 tests to show what can we expect, what can you expect if you buy PowerPC PC, what can you expect for the system performance. So the first test which I did was an Nginx test. I was trying to find a scenario which could show differences between Intel CPU and Power8 core. So I started looking at and I found a very nice tool. It's called WRK, which the main purpose is to generate requests per second. So we can stress the Nginx and to see how many requests it is able to handle depending on the threads and on the workload we provide. So the Nginx was a very simple configuration. It was almost like out of the box with just small tuning, like disabling logging to file because it sucks and makes the Nginx slow. But if one knows the Nginx better and knows some other hacks, configuration hacks which he or she could use, then we probably get even more numbers, even higher numbers. So that is the curve we got. The orange one is the Intel Core i5 running the FreeBSD, and the blue line is the Power8 running FreeBSD. The Intel one has, it's not, we try to limit the number of Nginx workers to the actual number of CPUs the system offers. So we are limited to 8 on the Intel, but on Power8 we used up to 16. We didn't want to use SMT threads because we know they are impacting performance, so we were only using 16 because 16 is the number of physical cores we have in the system. So we can see that we are topping about 90,000, 87,000 requests per second. And what we can see that the PowerPC version of FreeBSD scales a little better. We have no comparison on, I don't know, didn't run comparison tests on more decent Intel machine having 12 or 20 cores because I didn't have one. So this is why I was limited only to 8 CPUs. But it seems, it doesn't seem that the Intel version scales much better than the PowerPC does. The other test I did was the NVMe IOPS test. There is a nice tool called FIO, which stresses the IO subsystem. It's quite a good tool because it not only stresses the kernel, but it also heavily utilizes libc and user space. So we can benchmark almost everything using this tool, the whole complete stack, just from the user space up to the kernel level, up to the interrupts, and etc. What we found is that the FreeBSD is 50% slower than the Linux. It still offers quite impressive performance to 250K IOPS per second. It's a pretty huge number, but the Linux version is better. In this test, we compared Linux on Power8 with FreeBSD on Power8. If you're asking me why there is a difference, well, this is something I was already talking about. On FreeBSD, we are using very old toolchain. We're using very old libc, which is not optimized to work on Power8. The libc, which is included in the FreeBSD distribution, for example, doesn't have the memcopy using SIMD instructions. So the memcopy there is very slow. We suspect that moving to some more decent toolchain will make the gap between FreeBSD and Linux a little smaller. And there is a plan for replacing the toolchain, but I think it's Edmaster is responsible for some GCC build for the Power9 project. So we probably will still have a chance to use it for Power8, but I think we need to wait a couple of months to make it happen. So this is going to the end of the presentation. From this point, I would like to thank to all of the guys who are involved in the project, especially for Nathan Whiteford, who created the all initial work and all support for emulator. Also for Kevin Bowling from IBM Networks for organizing the project, and from Sam Montoya at QCM for providing hardware both for us and for FreeBSD Foundation. So if you have any questions, I will be very glad to answer them. Yep.
I have a question regarding...
sorry, please use microphone.
Oh.
Slow. Yeah.
Thank you very much. My question is about GOC bug and regarding this intelligent linker optimization. Is it possible to tell to linker to avoid optimization? I mean, this merge and split of talks.
I don't know if it is possible, but I think it will be impractical, because if you have a separate TLC for each function, if the kernel will not optimize the number of TLC tables in the system, you will end up in the binary having like 100 megabytes, where the 2 megabytes is the code, and the rest is the place reserved for TLC tables. So this is why the linker needs to perform optimization, because you need to save space in the binary.
Yes, but maybe we have another bug with TLC in another place, not only in switch.
Yes, there is a case, but it's not very unlikely, because scheduler switch is actually the only place which modifies the stack pointers. So I would be very surprised if this kind of bug would exist somewhere else.
Thank you. And another question: what's clock rate CPU frequency of Power8 processor? Is it still very high? Something like 5,
No.
4? No.
It's like 2.5, 2.6 gigs.
Thank you.
Okay, so if you have any other questions, I will be in lobby and I will be in the conference for the rest of the next 2 days. So if you have any chance, we can chat, you can grab me and ask about anything. So thank you very much for your attention, and have a nice day.